Hi, in this video, I will be showing you problem number 19 of chapter 16, section 3. Show that the line integral is independent of the path and evaluate the integral. Integral over c 2x e to the negative y dx plus 2y minus x square e to the negative y dy. C is any path from 1, 0 to 2, 1. So the first part is to show that the line integral is independent of the path, and the second part is to evaluate the integral. So given the line integral over c, which is 2x e to the negative y dx plus 2y minus x square e to the negative y dy is also equivalent to another form, is same as the line integral, is in the form p dx plus q dy, where p is 2x e to the negative y and q is 2y minus x square e to the negative y. So now, this integral in the form p dx plus q dy is same as integral f dot dr, where f has components p, q and dr has components dx, dy. So if you take the dot product, you are going to get p dx plus q dy, which is the integrand in this form. So this is another form of finding the same line integral we have been talking in this section. So integral over c f dot dr is independent of the path if f is a conservative field, or in other words, for a conservative field. In other words, f, here to show that integral over c p dx plus q dy is independent of the path, we have to show that f is a conservative field. In other words, we have to show that dou p by dou y equal to dou q by dou x. In other words, a partial derivative of p with respect to y is same as partial derivative of q with respect to x. If p and q have continuous first order partial derivatives over R2, and if partial derivative of p with respect to y is same as partial derivative of q with respect to x, then f is conservative. So this is the requirement, this is the condition for f to be conservative in a two-dimensional space. So we have another formula for conservative field when f is a function of three variables. So now let's compute dou p by dou y, or partial derivative of p with respect to y, which is same as partial derivative of 2x times e to the negative y with respect to y. So which is same as negative 2x e to the negative y. If you do dou q by dou x, or partial derivative of q with respect to x, is partial derivative with respect to x of 2y minus x square e to the negative y, which is also equal to negative 2x e to the negative y. So dou p by dou y is same as dou q by dou x. That proves that f is a conservative vector field. Dou p by dou y equal to dou q by dou x. Thus f is conservative. If f is conservative, automatically the integral is independent of path. The line integral is independent of path. Now next part is to evaluate the integral. So if f is conservative, there is a potential function f such that the vector field f is equal to the gradient of the lowercase f. There is a potential function f such that f equal to del f, the vector. So if we compare the components, p comma q is equal to fx comma fy. So fx equal to p, which is equal to p of the function is 2x e to the negative y, and fy is the q of the vector field f, j component, which is 2y minus x squared times e to the negative y. So integrate with respect to x, then you get 2x squared over 2e to the negative y. This being a function of x and y, the constant should be a function of y. Now we will differentiate this with respect to y and compare the two fy's. If you differentiate this with respect to y, so you will have negative x squared e to the negative y plus g prime y. So if we compare the expression from step 4 and f of y here, we can equate the f of y's, f sub y's. If we equate the two f sub y's, we get negative x squared e to the negative y plus g prime y equal to 2y minus x squared e to the negative y. So we get g prime y equal to 2y. Integrating this with respect to y, you get 2y squared over 2 plus a constant. Then we plug in this gy into f in step 3. Substituting g of y into f in step 3, we get f of xy equal to x squared e to the negative y plus y squared plus c. Thus we get the potential function for the conservative vector field f. Now the second part is to evaluate. Finding the potential function makes the problem very easy to evaluate the second part of the integral. So part 3 is to evaluate the integral. So here we have shown integral over cf dot dr is equal to integral del f dot dr, where f is the potential function, lowercase f is a potential function. Then by fundamental theorem for line integrals, this becomes lowercase f, potential function terminal point minus potential function at the initial point. Integral over cf dot dr is integral over c del f dot dr, just f at final minus f at initial. So where f is what we found out in the previous slide, which is this x squared e to the negative y, y squared plus c. So here we see integral over cf dot dr is integral over c 2x e to the negative y dx plus 2y minus x squared e to the negative y dy, which is nothing but f at the terminal minus f at the initial. So we find out these values plugging 2, 1 into the function f that we already found out. It will become 4 over e plus 1 minus 1, which is 4 over e. Hope this video helps.